the principles of the principles of principles of inclusion and exclusion. Inclusion and exclusion. And exclusion. Inclusion and exclusion. Mathematical induction. Mathematical induction. Mathematical induction. Mathematical induction. Okay, contents, objectives, introduction, basic continuity principles, some of principles. So introduction, at your school level, you have to study the concept of sets, the type of sets, a cardinal number of its sets. You have also studied about the operation on sets like union, intersection, and complementation. In this unit, uh, you will study about the generalized concept of counting the number of elements in the union of any given number of sets known to be principles of inclusion and exclusion. Some applications of these principles will be studied both fictionally and numerically. At the same time, you will be also learn some basics of counting and importance of induction, mathematical induction of the application. Basic counting definitions. Basic counting definition. Definition. Basic counting definition. Now, while we counting 1, 2, 3, these numbers are called counting numbers or natural numbers. Yeah. So the sum rule. The sum rule. The sum rule. The sum rule. If A is a union of pairwise disjoint sets, if A is a union of pairwise disjoint sets, U is the union of is the union of pairwise disjoint sets. Disjoint sets. Pairwise disjoint sets. Pairwise disjoint sets. So A1, comma, so on, AN, the absolute number, mod A equal to mod A can be written as modulus of A1 plus modulus of A2, modulus of A2 plus so on plus mod AN, mod AN, mod AN. Here A1 into are non-empty sets having no common elements. Here A1, comma, A2, etc. AN are non-empty sets non-empty, non-empty sets, non-empty sets. There is no common elements. There is no common elements. Common elements. There is no common elements. Common elements. This is known as some rule. This is known as some rule. It's known as some rule, which is known as the principle of disjunctive counting, which is known as known as principle of principle of disjunctive counting. Disjunctive disjunctive counting. Disjunctive counting. Principle of disjunctive counting. The same principle can be stated in terms of events or events. So example. What is the example? In how many ways we can get a 4 or 8 when two disjunctive dice are rolled? Here observe the 4. For 4, we are getting means x1 plus x2 equal to 4. Means 2 rolled, 2 dice are thrown. You have to get 1, comma 4, 2, comma 2, 3, comma 3. So x1 plus x2 equal to 8. 2, comma 6, 3, comma 5, 4, comma 4, 5, comma 3. And 6, comma 2. Number of ways are 4 or 3 plus 5, so 8. This is 3, this is 5. Total number of ways are ticketed. So next product rule. Next product rule. Product rule. Product rule. Product rule. If A and B are two non-empty sets, definition. If A and B are two non-empty sets, two non-empty sets. A and B are two non-empty sets. Then Cartesian product of A and B. Then Cartesian Cartesian product of A and B. Product of A and B. Cartesian product of A and B is denoted by A cross B. Is denoted by A cross B. Denoted by A cross B. And is defined as defined as defined as defined as A cross B equal to A comma B such that A belongs to capital A, small b belongs to capital B. Capital B. Instance, let us consider for example, A equal to 1, 2, 3. A equal to 1, 2, 3. B equal to 4, comma 5. 4, comma 5. So A cross B equal to A cross B equal to 1, comma 4, 1, comma 5. Now 2, comma 4, 2, comma 5. 3, comma 4, 3, comma 5. 3, comma 5. So here A cross B equal to. So here n of A equal to n of A equal to mod A. How many elements are there? 3. N of B equal to mod B. How many elements are there? 2 elements. So n of A cross B, n of A cross B equal to mod A cross B, mod A cross B. That equal to 3 into 2. That equal to 3 into 2. That equal to 6. Equal to 6. Next. A product result. Next. Theorem important. The principle of inclusion and exclusion for two sets. Theorem. Theorem. The principle of inclusion and exclusion. The principle of inclusion and exclusion. Inclusion and exclusion. 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 The principle of inclusion and exclusion. For two sets. Statement. If A and B, and B be any two non-empty subsets, be any two non-empty sets, any two non-empty sets, two non-empty sets A and B, two non-empty sets of the universal set U of the universal set U. Universal set U. Universal set U can be represented by Venn diagram as below. Can be represented represented by Venn diagram. Venn diagram. Venn diagram. Venn diagram. Here. The universal set. This is set A. This is set B. This is A intersection B. This is A intersection B dash. A intersection B dash. A intersection A bar intersection B. A B bar. A intersection B bar. Here, A bar intersection B. Okay. Using this diagram, we'll prove the theorem. Prove the theorem. The principle of inclusion and exclusion when we are not in presets. Presets. P and B are subsets of universal set. This is O. O. Theorem. This is principle of inclusion and exclusion for set. If A and B, A and B, yeah, are subset of universal set U. Subset of universal set U, subset of universal set U. Then modulus of A union B equal to mod A plus mod B minus modulus of A intersection B. A intersection. A intersection. Here, if A intersection B bar, here, A intersection B bar, comma, A bar intersection B, A bar intersection B, A bar intersection B, and A intersection B are mutually disjoint sets. Are mutually mutually disjoint sets. 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 Then modulus A union B equal to modulus of A union B equal to modulus of A union B equal to modulus of A intersection B bar plus A intersection B. A intersection B plus modulus A bar intersection B. A bar intersection B. That equal to A minus modulus of A minus A intersection B. A minus A intersection B plus A intersection B. A intersection B plus B minus A intersection B. A intersection B. A intersection B. So here, what happens? These two get cancelled. These two get cancelled. Then we can write mod A plus mod B minus mod A intersection B. Mod A plus mod B minus mod A intersection B. Mod A intersection B. Mod A intersection B. So hence prove. Hence prove. Suppose mod A intersection B equal to null set. That means mod A intersection B equal to 0. Then above theorem becomes A union B. A union B. That equal to mod A plus mod B, mod A plus mod B. Next. Next. Theorem is pigeonhole theorem. Pigeonhole theorem. Pigeonhole theorem. Most important for 10 marks, long answer time. Theorem. Pigeonhole theorem. Pigeonhole theorem. Pigeonhole theorem. Let statement. Let M1 and are positive integers. Let M1, comma, M2, comma, Mn are positive integers. Positive integers. Positive integers. Positive integers. If M1 plus, if M1 plus, so on, Mn minus N plus 1. Number of objectives are put into M. Number of objectives put into N. N into N. Put into N. Boxes, then either the N boxes, then either the first box contains, then either the first box contains 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 at least M1 objects. At least M1 objects. At least M1 objects. Second box contains contains contain at least M2 objects. At least M2 objects. M2 objects. M2 objects. At least M2 objects. At least M2 objects. At least M2 objects. So on, so on. So nth box nth box contains nth box contains at least mn objects. At least mn objects. Objects. This mn objects. Mn object. At least mn objects. Mn. Mn objects. Proof. Proof of theorem. So we prove this by the method of contradiction. So we prove this by method of contradiction. Method of contradiction. Method of contradiction. Method of contradiction. Let P be the statement. Statement. Let P be the statement. Hence M1 plus M2 plus Mn minus N plus 1 minus N Mn. Number of objects are distributed into n by n. Number of objectives number of objectives are number of objectives OB JEC TI VES. Number of objectives are distributed into n boxes. Are distributed okay, into distributed into n boxes. N boxes. N boxes. Let Q1 be the statement. 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 The ith box contains at least the ith box. Ith box. Ith box contains ith box contains at least mi number of objects. At least mi number of objects. Objects. Number of objects. Let Q equal to let Q equal to Q1 or Q2, Q1 or Q2 or Qn. Now to prove P implies Q, to prove P implies Q. P implies Q. P implies Q. Assume the truthness of 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 P and negation N negation Q. P and negation Q. Here negation Q1 means ith box contains less than ith box contains ith box contains less than mi number of objects. Less than mi number of objects. Mi number of objects. Number of objects. Similarly, minus Q ith number of m minus 1 objects minus Q1 one first box, negation Q, first box contain less than or equal to M minus number of objects, so on, so on, so on. Negation Qn, negation Qn, negation Qn. The nth box contains the nth box, nth box contains, nth box contains, nth box contains less than or equal to Mn minus 1, less than or equal to Mn minus 1, Mn minus 1. Number of objects, number of objects, number of objects. Adding all these we get adding all these we get we get we get all these we get negation Q, negation Q, negation minus negation, negation and minus Q minus negation Q2, negation Q2, so on and minus negation, negation Qn, minus negation Qn. So negation Q, the total number of objectives, the total number of negation negation Q, negation Q, the total number of objects, the total number of objectives 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 that are distributed into that are distributed into distributed into distributed into distributed into distributed into distributed into n boxes is less than or equal to M1 plus M2 plus Mn M1 minus N. But the total number of objectives, what total number of objectives, number of objectives that are distributed into distributed into distributed into n boxes is n boxes M1 plus M2 plus M3 plus Mn minus N plus 1 minus N plus 1. N plus 1 is less than or equal to, that is M1 plus M2 plus M3 plus so on Mn is less than or equal to M1 plus M2 plus 1 plus Mn minus N minus 1 is less than or equal to 0 is less than or equal to. This is contradiction. This is contradiction. This is contradiction. This is contradiction. Hence P and negation Q is not true. Negation Q is not true. Hence, P implies Q is true. Is true. Is true. Is true. Hence proof. This is the complete proof of the theorem. Okay. Next. Second form and third form is there, do it as homework. And also mathematical induction. Basic induction, n equal to 3, n equal to 3. Already you discussed it in the lower classes, 11th and 12th standard. So, example. Here 4.6.2, 4.6.3, 4.6.4, 4.6.5. If you practice these 4, you'll get 10 marks. Long answer type. Long answer type. Long answer type questions. Long answer type questions. Okay. Each carries 10 marks. If you practice these 4 theorems or probe mathematical. Then you will get 10 marks. Right, most important. Thank you very much. Dear students, so you read these for full discussion, two theorems, and for the examples. And okay, we'll meet tomorrow. We completed 4th unit. We'll discuss tomorrow 5th unit. Thank you very much.